Okay, so what we're going to do now is wrap up the end of chapter 9. We have three relatively short chapters to go, or sections, I should say, 9, 8, 9, 9, and 9, 10. And these are very interesting topics, but they're not extremely complicated. So we'll get through these fairly quickly. And some of these you'll see again if you do find yourself in Calc 3. In particular, the Taylor series will prove to be very useful for other applications that you may run across. It's used fairly regularly in certain disciplines like economics, let's say. Anyway, so let's begin with the notion of the power series. And so the power series, um, the formal definition is, let me write this down. Any function that takes the following form. Here we go. So here's what a power series means. Ah, hold on. My tablet does not seem to be connected right now. Okay, that'll do it. Right, here we go. Maybe not. No, you know what it is? I'm trying to use Bluetooth. Um, Sometimes it works and sometimes it doesn't. Hold on one second. Yeah, I find the Bluetooth is 100% unreliable, but sometimes that's the only choice you have. But now, see if I rearrange my external drives, I can plug this thing in. All right. So even this thing should work when it's plugged in. Yeah. Oh, there it is. Okay. See, the funny thing is the light was on and everything, but it just wasn't working. So, but that's pretty normal for this tablet. So anyway, here we go. Power series. It can take one of two forms. Okay. So it's a series, as the name suggests, which means we're adding up an infinite number of terms, starting with zero. And as long as it takes the form an x to the n power, it is therefore considered to be a power series where an is a constant. Okay. And of course, this has a lot of different possibilities here for what we can sneak in there for the constant. If, on the other hand, it's written like this, then it's still a power series, but specifically, it's said to be centered at C. Now, in principle, the one directly above it is also centered, but it's zero. Okay, so in effect, I mean, they really are the same thing. One is a special case of the other. So once we have this set up, there are ways that we can determine how to use power series to represent functions. And sometimes that can be very, very helpful in finding solutions to very messy problems, or sometimes just finding approximations, depending on what we're trying to accomplish. Anyway, so let's see our first example. Um, so they're showing us here a classic example of a power series representation of a function that we know very well. E to the x is actually equal to what you're seeing there, 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way out. If you add up the infinite number of terms on the right-hand side, you'll get exactly e to the x. Okay, that's what it actually, it's a way of expressing it. And there's many other functions that we can do the same thing for. So, here we go. So there's the definitions that we just looked at. And here's some examples. And you can see they can get very complicated because, like, for example, here, n factorial is a constant. And so they want you to see that this first one has a center of zero, okay? Because of the way it's written, if you think of, let me just quickly make a note of this here. Remember, the basic form would be, well, here, what we've got is 1 over n factorial. And of course, all that means is that a to the n, sorry, a subscript n is equal to 1 over n factorial. So in other words, this qualifies as a power series. But if you notice, I don't have a C here, so that means that this one is centered at 0. And one of the implications of this is that it's guaranteed to converge to a specific sum as long as x is equal to 0. But there's other important details here we need to know. For example, if we look at the second one, the way this one is written, they're trying to illustrate that since the center is subtracted, here what we have is that implies that C must be -1. And then the next one they have is just the opposite. So again, because we can think of this as AN, it must be the case that the center is 1. Okay, radius and interval of convergence. So here's a function. The function is a power series. And they would like us to notice that the domain here is all x such that the power series converges. Now, when it says converges, what they really mean is this. Depending on what x or c we choose, we want this infinite sum to equal some specific constant. If the individual terms are getting larger as we increase, as n increases, then there will be no such sum, and the series diverges. If the terms themselves are getting smaller, as we keep adding them, they will converge to a specific constant, and then that means the series converges. Okay, so some of these series, the terms get larger and larger, and therefore they diverge. They're not approaching a specific sum, or in other cases, they are getting smaller, and they are, in fact, the sum, in fact, is converging to a specific value. So in all these cases, we'll be interested in knowing if it converges or diverges, and if so, to what value. So here, for example, every power series, are proving that every power series converges at its center, because if x equals c, then all we end up with is a0, which means that's the constant that they add up to. So this introduces this notion of radius and interval of convergence. For some of these series, they only converge at a single point, which is what you're seeing here, which is the center. And so in some cases, we have that point. The C is the center. Okay, so in other words, if they only converge at one point, it's going to be the center. Okay, but sometimes there's a range within which it converges. So let's say here's C. R is the radius. And so if there is such a radius, we could write this as, oh, I see what they've done. All right. Just put R on either side. So in other words, this is R. Therefore, this must be R plus C and or let's write it like this, C plus R and C minus R. Okay. So that's the second possibility that the series only converges within that range. In other words, this is the interval then of convergence. R is the radius of convergence, and that defines the interval of convergence about the center, C. And then, of course, in some cases, the entire real number line um, is the interval of convergence. Okay, everything. Okay, um, let's see. Of course, now we have to figure out how to find these. So here they're going to ask us to do exactly that. Let's write this down. N factorial x to the n, which implies that a is this n factorial. And if you notice, the center is 0 because of the way it's written. And they would like us to notice that, oh, and I forgot to write this over here. So the first term will be 0 factorial. Uh, all right, hold on. Now that's actually, this is f of x. Let me rewrite this slightly. And then we'll get to f of 0. This is fine, but then we have to evaluate it at 0. So the bottom line is it ends up being 1. 0 factorial is 1. Um, so we're treating this as 1, it looks like, because 0 to the, okay. But so it ends up being 1. And so in other words, it only works at 1, 0. Now, here they're reminding us that how can you tell if a series is convergent or divergent? We have this test called the ratio test, which in principle says this. So what we have here is the ratio of two consecutive terms. Actually, no, one is in the middle. Hold on. Let's put one, greater than one here. And this is the ratio test. So here, um, they're using this as our example. So you notice how they're rewriting it slightly, and u as a function as opposed to a constant. And for that last example, what we're trying to do here is rewrite the entire expression as u to the n. Okay, so therefore, u to the n plus 1 would be n plus 1 factorial. And then x to the n plus 1. U to the n, of course, is just n factorial. X to the n, no. What is this equal to? All right, well, that's a good question. So let's use some specific examples. Let's say if n is 5, you're going to have 6 factorial over 5 factorial. And that means, which means there's a lot of canceling out going on here. And you're just left with 6. So therefore, in the general, this just reduces to n plus 1. Okay, so we're going to have, and of course, x to the n plus 1 over x to the n is just x. So when we take the limit, we end up with infinity. Okay, which means that the series diverges. And that means the only place it can converge is at its center. Okay, which in this case is 0. Everywhere else it diverges. So its interval of convergence would just be that one point. And then it formally also means formally that this R, the radius of convergence, would be defined as zero. All right. Endpoint convergence. Well, if you look at these intervals, you'll see that they have endpoints, at least in this case, and we may need to test for convergence at the endpoints as well. We want to know if, for example, they are included in this interval or not. So in other words, they're going to show us in the next slide several cases that we could encounter. We have, besides the center single point at which it converges and the entire real number line, with the radius of convergence, there's several possibilities. So quickly, let's see. They're starting with this one. The round brackets means that that number does not actually get counted in the interval. So here, neither endpoint is it's not convergent at either endpoint. Everywhere in between, yes, but not there. But then we have this, the opposite case would be this. Those square brackets mean that they do get counted in the interval. And then we have everything in between. We have one side is included and the other is not, vice versa. So all the other possibilities are listed here. And so let's take a look at this one. So remember the way these work, it can, by the way, it can start at 0 or 1. Every case is different. It's still an infinite series, even if it starts at 1. So therefore, what we actually have here is 1 over n x to the n. So that means our an is 1 over n. And the center is 0 because we're not subtracting anything from the x. So they want us to let u be written this way so we can easily take the limit. Okay. So un plus 1 would be 1 over n plus 1, x to the n plus 1. And that ratio, so we can see what's going to happen with the x's. What about these? Well, we can rewrite this as 1 over n plus 1 times n over 1. So we end up here with, okay, and then when we take the limit, um, now in order to solve for this limit, we're going to have to do something different. We're going to divide the numerator and the denominator by n. Okay, you'll see why. Um, so that when you do take the limit as x goes to infinity, this goes to 0. We end up back with x. Oh, actually, I forgot the absolute value sign. Sorry about that. Um, yeah, the test that we need is actually the absolute values. All right, and I think I left them out up here too. Well, I mean, I wrote it in over here, but then I guess I sort of lost it. So yeah, let's put it back. There we go. All right, we're good now. So this is my R. R is 1. And since the center is 0, the interval of convergence would be. Now, here's the problem, though. We can't be sure that the endpoints are convergent or not. We have the interval, but we have to test the endpoints. So when x equals 1, let's go back to the original series. It's x over x to the n over n. Oops, that's cubed. Okay. Okay. So this is going back. This was introduced. I forgot what chapter this is. This is a so-called harmonic series. Divergent. It's 1 over x to the p. All right. Anyway, so when x is -1, on the other hand, now this is different because you notice how it alternates back and forth between adding and subtracting. I mean, it's the same numbers, but half of them are negative and half of them are positive. So because of that, this sum is going to converge. And so um, the series converges. See, this one is just going to go to infinity at x equals -1, but not x equals 1. So we end up with this. So here it's a yes, and here it's a no. And of course, you're supposed to fill in this part too, so you can see that we're talking about everything from the endpoints inside. Okay. So that's what it looks like. This is my interval of convergence. And of course, so the center is 0, the radius of convergence is 1. Now, believe it or not, you can actually differentiate and integrate a power series. There's a set of rules they're going to give us, just so we can see what's going on here. Let's just copy these so we can see them. And this is just based on the power rule, okay? And then for the integral, we have again, just the power rule applied to this function, except that it's integration. And of course, we don't forget the c. And this is how it works. In case you need to take a derivative or an integral of a power series, here's how it's done. All right. So that was 9-8. What's going on in 9-9? Let's see. No, this is the one that I said that you're going to get a lot of use out of this one. 9-9, I don't, I forgot what the title is. Oh, how to represent a function by a power series. Okay, so this is something else you may run into. And certain results will be much easier if you're able to do this properly. Some of these results show up quite often in certain disciplines like finance, for example. Um, this could help us figure out, for example, how rapidly money grows in a bank account and that kind of thing. So a function that looks like this, um, and again, this is known as representation of functions with power series, which can save us an awful lot of grief. They also can use these to derive important results. When you see a formula, for example, you might find out later on that it was derived with a power series. So, it's kind of interesting to keep an eye on that. Representation of functions of power series. So specifically here, they're going to focus on the so-called geometric power series. There's also an addition, additive power series, or I'm sorry, arithmetic power series, but this is the one that we really see the most often. So if you see a function like this, you immediately think geometric power series. And the way it's written in general is, now if you notice here, A doesn't have a subscript. It's a constant. Every term has the same A. But we do have a variable R raised to the n power. And it turns out that as long as the absolute value of R is strictly less than 1, this infinite series reduces very nicely to A over 1 minus R. It's very helpful. Okay, so what are we going to do with this? Um, all right, let's find a geometric power series centered at 0. 4 over x plus 2. So we got to look at this and say, well, how does it relate to this? So we write the function as A over 1 minus R, like we have here. Compare it to 4 over x plus 2. And they're going to have us, looks like we're going to divide everything by 2. But they're going to, okay. They're going to, because remember, it needs to be in this form. And so therefore, A is 2 and R is negative x over 2. And then we know that from here, R, uh, this is going to lead us, okay. So when you compare it here, you're going to have 1 minus x over 2 plus x squared over 4, et cetera, et cetera. And so it appears to be converging because we're adding and subtracting, and as long as x is, well, x over negative x over 2 is less than 1, we have convergence to a specific sum. And so even though it's strictly less than 1, um, 2 is the radius of convergence. Out here, this 2 we factored out, and the center is 0. Now, algebraically, we can treat these in a very straightforward way. You can, for example, multiply the whole thing by a constant. You can add them together. You can subtract. You can add them. Now, here they decided to pick a very messy example where they want us to break it up into two terms with partial fractions. And when they do that, you can see how this turned out. They're converting it into a over 1 minus r. And we end up with this result down here. And then that gives us a radius of 1 and a center of 0. All right. Now, the last one of these chapters is the one that I personally find the most interesting, the Taylor series and the Maclaurin series. They're an extension of what we're doing here, but you can use them for so many different things. Let's say, for example, you have a very high order polynomial and you need, let's say, a quadratic approximation to it. This is how you would do it. Okay. And so for certain disciplines, again, this is something that you might run into fairly regularly. Uh, like let's say you've got this scary high order polynomial and you're interested in approximating it with a quadratic function, let's say over this interval. You can use a Taylor series to come up with a quadratic function in this interval that does a very nice job of approximating this messy polynomial. But that's just, of course, one of many applications of it. And these two series, they're very closely related to each other. One is a special case of the other, so they're not really two different things. So this is how it works. Um, right here, actually, let's bring it onto this page. This is the actual formula for our Taylor series approximation. Oops. So this is the pattern that we have f of c, f prime of c, x minus c, and then actually, I'll tell you what, let's write it out a little more clearly here. All right, so I hope the pattern is more clear by writing it that way. In practice, we rarely have to go out past the squared term, but you never know what you might run into. So this is a Taylor series expansion. And you can use it to essentially just approximate any polynomial you might run into. The number of terms you use depends on how much accuracy you really need. If c is equal to 0, which is the center, then this is known as a Maclaurin series. Okay. Okay, they're gonna test us by having us do a Maclaurin series about the sine of x. So to get started, now that implies that the center is 0. So to get this ball rolling, we'll need some derivatives. Oh, actually, I think the way they encourage us to do it is all right, let's try it this way. We'll start with f of x. Now, it turns out when you get to the fourth derivative, now some books write it with a four, some books use Roman numerals. You're basically back to where you started. Now, we're going to need to evaluate these at zero, but that's not going to be a problem because we know that the sine of zero is just zero, and the cosine of zero is one. So that means that we have, and then f4. And then, you're just going through the same cycle over and over and over again. All right. Let's see. Now, let's grab the definition of the Maclaurin series. This is Taylor, but we can change those to zeros. I don't remember how far they expect us to go with this. Um, it looks like, oh my God, they really went out there pretty far. All right. That's right. We don't need to go berserk. We just want to get a little practice here. All right. So f of zero is zero. F prime of zero is one. F double prime of zero is zero. F triple prime is negative one. 3 factorial is 6, of course. And it just goes all the way out. And so they are showing us that it's here, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and then go on and on and on. Then they simplified it into this form so that they could take the limit, the ratio test rather, and they found that this converges for all x. Okay, so what else do we need to know? For if the limit of r equals n, Rn equals 0 for all x in the interval, the radius, the radii, the Taylor series converges and equals f of x. Okay. So here, this is what I was talking about before, how you could use For example, a third order polynomial to approximate this. These are the two terms that we came up with, x minus x cubed over 3 factorial. And you can see it does, at least over a limited range, a pretty good job of approximating the function y equals sine x. Okay. A binomial series is it's a special case of what we were just doing, where we have 1 plus x to the k. So we're going to use a Maclaurin series on this. And you can see it's getting to be kind of a mess. So, by the way, this is a typo here. That's supposed to be dot dot dot. So we end up with the ratio test. They didn't show the results, but they took the ratio test with a ratio of convergence of 1. So we end up in the interval negative to positive 1. They've got some results for us to look at here. But really, this is the interesting one where you can see that, for example, log x can be written like this. This one we saw earlier, e to the x can be replaced with this series. And there's quite a few others too. In fact, it's possible, I didn't check. There's a list of these in the back of the book. A lot of calculus books do that. So, all right, anyway, I think that's enough to get through the WebAssign problems. So, of course, the class ends on Monday, so we don't have all the time in the world, but you can just make sure all the exams are done by then and all the assignments. And then the grades will be, I can put them in, let's say Tuesday or Wednesday at the latest, but I don't know how long it'll take before you actually see them. So if you're desperate to know, you can send me an email and I'll write back to you with your grade. But, you know, I have no control over how quickly heliotrope feeds the grades into the system and gives you your final results. So anyway, so that's that. Now, I don't know if you're taking Calc 3 or not, but certainly this is one of the topics that you'll find to be very useful there. Calc 3, what happens is you have a lot of multivariate functions, and they spend some time with what's called linear algebra or matrix algebra and a lot of other specialized topics. In a lot of ways, Calc 3, a lot of people believe that it's easier than Calc 2, and I think that's about right. But it should be interesting. All right. So I'm glad you were able to attend this class, and good luck with your future math studies. So goodbye.